So we have a time of concentration of 35 minutes. Find the intensity. So our intensity is 120 over T plus 20. So the intensity is equal to 120 over 35 plus 20, which is equal to 120 over 55. 120 divided by 55 is 2.18 inches per hour. So what that means is the basin is handling an equivalent rainstorm equal to 2.18 inches per hour. It doesn't matter whether it's raining for 10 minutes or it's raining for 6 hours. You're never going to get more water into that basin than an equivalent rate of 2.18 inches per hour. This value has nothing to do with the amount of water that the recharge basin is designed for. The recharge basin will be designed to handle typically 5 to 8 inches of rain. That's over a 24-hour period of time. Flow rates of intensities of 2.18 inches per hour are typically going to be shorter duration rainstorms. You're not going to be seeing stuff lasting for hours and hours of rain. Okay, let's take a look at our next one, which says find the intensity based on water running to a drain from a point 700 feet away across bare soil on a slope of 2%. So for this one, we have our second nomograph, which is time of concentration. So when we do this time of concentration, we have 700 feet across bare soil, which means we're going to start up here. And we have to get across that pivot line. So that looks pretty good. Okay, we hit the 700 feet on the length of the strip in feet. We went right through the bare soil and we come to the pivot point. At that pivot point, we now have to cross through whatever the percent slope of that land is. And these are numbers that you would actually figure out based on reviewing a site plan. This is survey data you get ahead of time before you start the actual design. So this isn't something that's always just given to you. So now from that pivot point, we go through 2%. And again, with a straight edge and a ruler, it's much easier to do that. It's not cooperating. There we go. That works. And it looks like our time of concentration is 15, 16, 17, about 16.5. So T is equal to 16.5 minutes. That means our intensity would be equal to 120 over T plus 20. Intensity would be 120 over 16.5 plus 20, or 120 over 36.5. And that would equate to 120 divided by 36.5, or 3.28, actually 3.29 inches per hour. So for this problem, we have a catch basin with a storm drainage area of 73,000 square feet. The runoff coefficient for the area is 0.4. The intensity is 120 over T plus 20, which would be equal to 120 over 18 plus 20. That is an intensity of 3.16 inches per hour. So when we go to figure out how much water is actually going into the basin, Q is equal to CIA. Q is equal to 0.4 times 3.16 inches per hour times 73,000 square feet. And what's the units we need for that? That's got to be acres. So 43560. 43,560 square feet per acre. So Q going into the basin will be 2.12 cubic feet per second. Now that we have a Q equal to 2.12 CFS, we want to keep the velocity around 5 feet per second, and the slope is around 0.0200. We're going to try and hold the slope and let the velocity float a little bit. So let's go down to our nomograph over here. And on this nomograph, I have my Q at about a little over 2. Bring it down a little bit more. And I put my velocity at around 5 feet per second. And when I do that, I get a diameter of 9 inches. Now that pipe is way too small. We need to be at least at 12 inches and ideally at 15 inches. So what I'm going to do on this one is I'm going to keep my slope at 0.02. See if this works. 15-inch diameter. Slope of around 0.02. And that gives me a velocity of 7.6. V is equal to 7.6 feet per second, holding that slope of 0.02. And now the Q is equal to around 9 CFS. So by changing one parameter, it really changes how the entire pipe is going to function. So let's see what happens with that. So this now goes to 9. This now goes to, we say 7.6. And we're using a diameter of 15 inches. So let's prove this out based on the Manning equation now. V is equal to 1.486 r to the 2/3 s to the 1/2 over n. So solving for velocity, 1.486 times 15 over 12, that will be 1.25 over 4 to the 2/3 times 0.020 to the 1/2 power over 0.013. It gives us a velocity of 7.44 feet per second. So again, pretty close to what the nomograph is showing. We also want to find out what Q would be. Q would then use Q is equal to AV. So Q is equal to 1.25 squared pi over 4, and this is just our 18-inch diameter pipe as 12 inches times 7.44 feet per second. So 1.25 squared times pi divided by 4 times 7.44, 9.13 CFS. So what's happening is the pipe that only needs to handle 2.12 CFS will actually be capable of handling 9.13 CFS in the future. It won't see that much water now, but it can in the future.